Hi, welcome to the Paradox Developer Chat. I'm Tim Pavlik in a beautiful sunny afternoon here in Seattle, Washington. So I'm broadcasting from the University of Washington, which is where we make the Paradox game. And basically, the point of this chat is just an informal background into what we do here, why the game does what it does, how it works, and then I'm going to give a brief background on how our game has evolved from the first seedling version of the game into what it is now. And so at any time, you can ask, and then at the end, I'll be taking questions, but at any time, you can be asking questions via the Q&A app. If you're able to see that, there's a link below the video right now that sort of gives you instructions. It's a little difficult to figure out, but here, I'll go through it real quick. So feel free to ask questions right away, and I'll get to those at the end of the chat here. So basically, you want to mouse over the video, and there'll be a be part of the conversation link. And then once you're in that, there's going to be this apps menu, and within that menu is a Q&A app that you want to click on, and then you'll be able to ask questions in there. So without further ado, yeah, so I'm gonna try and set this talk to jargon level medium, because I assume if you're watching a developer chat, you want a little bit of jargon, but hopefully it won't go too far over the heads of people who are non-experts in the audience. So Paradox. So yeah, basically we have two groups collaborating to make this game possible within the University of Washington, within the computer science department here at the University of Washington. I work within the Center for Game Science. We make a lot of serious games and learning games. Serious game that probably is the most well-known here is Folded, the protein folding game. And we work side by side with Mike Ernst and the programming languages group. And so basically they generate the constraints that we use to represent the game, which is what I'll get into a little bit right now. So here, I've got a couple slides to show you guys. So here's what we do. We basically take a bunch of source code, and for us, we take, right now we're verifying Hadoop, which is a Java program that's used by a lot of companies, Facebook and Yahoo amongst them. And so basically what we're trying to do, the point of the crowdsourced formal verification program, which is funded by DARPA, which is why we're here, is basically to prove that certain pieces of software are free from security vulnerabilities. So basically, if you have, mission critical software that you want to make sure doesn't have like the Heartbleed bug or similar exploits so people aren't hacking your programs, then we're using software verification, and specifically using crowdsourced non-experts to make sure that that software is secure. And so for us, we're starting with Java code, and we're basically using a type system. So software verification, it's a little bit different from software testing. So software testing is basically running the code live in real time. You might know some software testers, and making sure that it behaves the way you want it to. Software verification, it requires a lot less man work in terms of testing, but it uses mathematical proofs. So the proofs themselves are much harder to generate, but at the end you have an assurance that the code is free from whatever security vulnerability you're looking at. So here's where we come in. So we start with source code, and a bunch of constraints are generated. So for us, we're doing operating system command injection, or OS trusted type system. So we're basically making sure that any commands that are being run on the machine that Hadoop is running on are trusted commands. So we don't want to be running potential user input or something that's come from a potentially malicious source. So what we have are a bunch of constraints that are generated. So this part of the group of the workflow is basically the programming languages group. They have an inference framework and they're generating all these constraints, and they send them to us here at the game side. And so we basically turn those constraints into levels and serve those levels to players so that non-experts can play the game. So basically, you don't have to know anything about software verification, but you're helping us solve these real-world problems. And then once the constraints are solved, go to the next slide here. So in the case where all the conflicts are removed, we have the ability to reinsert the solution that the players come up with into code and type check it. And if it type checks, we basically have a proof that that piece of code is free of that security vulnerability. So that code is good. In the case where it doesn't type check, so one of two options is happening. Basically, we have error reports that are being generated. And if the original program wasn't correct, which is what we're looking for, then we can identify parts of the code that may be vulnerable. The other potential reason why there are type checking errors is that our type checking model didn't closely enough represent where the errors were reported. And at that point, we can improve our type checking system based on these reports. Anyway, that is the background, but let me get to the game. So originally, we came up with the Pipe Jam game model here. So we started out as Pipe Jam. And so basically what we're doing is taking those programs and initially turning those into, oops, just close that. 1 second. So we've turned these programs into a set of pipes and balls flowing through those pipes. So here you can imagine that this is actually just a program, and these represent variables within that program. So, well, it's actually type annotations within the program. So we have all these type annotations, and we want to be able to determine what is secure and what's not. So here's an example of a pinch point. So this is a security vulnerability. It could be that this OS command is being used on the operating system, and wide in this case means it's either trusted or untrusted. So we're not sure where the input is coming from. So in the original game, we can adjust the width of these pipes, and that'll solve the level. And when we started out, we had the hypothesis that that we wanted to represent the game exactly as it appears in the code. So really, each board that you see here is a piece of code. So this would be like a method within that code. And then when there are method calls within method calls, you get something like this. So here's a board. So we have inputs. These are like inputs and outputs of the method. And so these are being fed into this other method. And so you have this sort of interdependency that you can see here. And so we liked this model, and this basically was the seed for the program. But eventually we thought we could improve the metaphor for the game and maybe make the graphics a little more interesting than, you know, this animation here. So we moved on to Traffic Jam, which was the next iteration of the game. So basically the process of converting the code to the game levels is the same, but the metaphor is different. So instead of balls and pipes, now we have cars merging into one another. And so traffic jams happen when for example, too wide of a traffic is of a road, sorry, is merging into a narrow road. So here you can see 2 cars are trying to merge into a 1-car road. So I need to resolve that conflict by opening that road up. And now I have eliminated that traffic jam. Yeah, so we seem to like this mechanic better, but one issue that we're running into is this, board within a board thing. So what can happen is that you can make an action at a distance kind of issue where if I affect this width of that road right there, it'll affect something within the other program. So here I can change the width of this this road right here, which is like changing the type annotation, but it actually messes up another board that I'm not even looking at. And we figured out that the problem was a lot harder to solve in that case. And so what we decided to do was just to eliminate this whole view of, a program, like basically looking at code, and unwrap or basically flatten out all of these constraint relationships. So anytime something was flowing into another program, we would just represent that as one big level. And so, yeah, all of these interrelated ones were expanded into one big level, and a new theme was chosen, and that's how we got FlowJam, which was our first Very Games game over here. So here you can see this is just a test level, but this could be, for example, like 2 different methods calling each other. So if method A was calling method B, and then method B was calling method A again, it would look something like this to reflect the interdependence. So this loop basically is what's going on. Yeah, so FlowJam. This is the version of the game without methods within methods, which we thought was more clear to people. And so you're still changing type annotations by clicking on these widgets. So clicking on this widget is the same as changing the size of the road or changing the size of the pipe in our previous versions of the game. So you can think of that as like anytime you change the width, you're basically saying that this type annotation, so this piece of code is either trusted or untrusted. And so you can see if you have a part of the code where you want to ensure something is trusted and you have a potential untrusted variable flowing into that part of the code, we have a problem because that could be a potential security issue. So here we have the ability to individually toggle all of these widgets, which is great, except when the levels get larger and larger, as they do with real code. So as you can see, it's scaling up now. Now we have like a dozen or so widgets to click on, and these are even some of our smaller levels. So we realized that asking users to individually click on widgets was a little cumbersome as the problem scaled up. So what we did was provide basically a small auto-solving function for the current version of the game, Paradox. So we wanted the ability to select smaller regions where the computer could just automatically pick what the best configuration is, because automated methods are much better at determining, like here we have only like 8 variables and they can each be one of 2 values, so like 2 to the 8 possibilities, right? Computers are much better than people at solving like very small optimizations problems like that. So why ask users to do something that a computer is better at? So what we did for the Paradox game, which I'm going to pull up right now. So yeah, here's essentially the same representation as FlowJam, even in terms of their light being narrow and wide being dark blue, except represented in a different way. So instead of variables flowing into one another, they're all being separated by these constraints. So basically, we have a set of, it's basically a part of the problem that, so this constraint involves these variables, right? And so for the constraint to be satisfied, like this one is right here, at least one of its branches has to be matched. So we can see this branch, which is dark blue, is matched by this. So this branch wants to be dark blue, but it's not. This branch leads to a dark blue variable that is apparently off screen, is not matched. And this one leads to wants to be light blue, but is not. So yeah, so this set of constraints is a little bit different in this version of the game. And what we gave them is the ability to use this optimizer. So this is the optimize brush, which you are probably familiar with if you played the game. So we can select, just a group of variables, and instead of manually toggling each one, so you can imagine in the old game having to toggle each one of these widgets would be pretty cumbersome. And so when we release, the optimal configuration is chosen. In this case, it's all narrow. And we also just want the ability to manipulate a bunch of variables at once. So just painting narrow in this case. So painting everything light blue, as is often a good solution. What we've noticed as a decent strategy for the current set of constraints that we have is to just paint a bunch of things narrow. And more often than not, that will get you a good solution. And then what errors remain, you can probably optimize away those errors depending on where they are and what depends on it. So yeah, that's how our game has evolved. And I'm not seeing any questions coming in. So let me just go through this last level here. So yeah, another feature that we've added is the ability for everyone to basically crowdsource the best solution using each other's assignments. So over here on the high score table, we've implemented, so we can see that user Tim Mimit has the best score, which is 99.92 right now. And so what I'm able to do as a user is to take this best score and load it up and see if I can beat that score. So in this case, there's just one conflict remaining. And let's see if I can optimize it away. Yeah, so the way the optimizer currently works, you can actually do more harm than good because it's basically optimizing what is in the current selection. So things just outside of that selection may actually turn into conflicts at the end of that. You can see my score has gone down just a little bit. So yeah, it looks like for this level, the best that we can do is Tim Mimit's score. So what that means is, since all the conflicts haven't been solved yet, we can reinsert that into code and figure out whether that was a legitimate security issue with a part of the code, or whether it was the way we represented the constraints within the game. And either way, that'll be extremely valuable for us. So yeah, that is Paradox. And if you have any other questions, feel free to write a question up on the forum at verygames.com and play our game Paradox at paradox.verygames.com. And we look forward to hearing back from you. All right, thanks for stopping by.